Okay, hello everyone. I am Wenqi from the Hong Kong Polytechnic University. In this part, I will be introducing the fundamentals of deep recommender systems. Driven by the recent advance in deep learning, there has been increasing interest in developing the deep learning-based recommender systems. So in this tutorial, we mainly focus on the deep learning-based collaborative filtering, where the goal is to employ the deep neural networks to enhance the user and item representation learning. The architecture of the deep recommender systems mainly consists of three main components. The first component is the embedding layer, which maps the role, user, or the item features. This in the high dimensional space to the dense vectors in a low dimensional embedding space. Then we can have the hidden layers, which performs the nonlinear transformations to transfer the input features and then the user item interactions. Here, we can use any kinds of deep learning techniques like the MLP or the convolutional neural networks or the recurrent neural networks, etc. At last, the prediction layer can make the predictions for specific recommendation tasks like the weighting regressions and learning to rank based on the representations from the hidden layers. And one of the most representative deep learning-based recommender systems is the neural metric factorization, which was proposed in IJCAI' 2017. Here in this paper, they explore the neural network architectures for the collaborative filtering. They devise a general framework to model the user and item interactions in two different ways, like the generalized metric factorization, GMF, and the multilinear procedures, the MLP. And that of this proposed framework, GMF applies a linear kernel, the inner product, to model the latent feature interaction, while the MLP use nonlinear functions to learn the interactions from the data. And the neural MF fuse the GMF and the MLP by allowing them to learn different set of embedding and get a more powerful model. In the second paper, we are going to introduce, here is the wide and deep model, which jointly trains the wide linear models and the deep neural networks to combine the benefits of the memorizations and the generalizations for recommender systems. And in particular, the right part here is a linear regressions for memorizing the seams feature interactions, which usually requires careful engineering on the course features. And this can help capture the non-linear interactions between the linear features. And the deep part is the feed-forward neural network for generalizing the unseen feature interactions through no dimension, low embeddings. In other cases, the many predicting tasks of recommender systems need to model the categorical variable, such as the user's demographics, the genders, or the occupations. These categorical features are usually highly sparse, So to effectively learn from such sparse data, it's important to consider the interactions between the features. We may all know the factorization machine, FM, is a popular solution for efficiently using the second order feature interactions. And in this slide, we introduce the new neural factorization machine, which can enhance the FMs by modeling the high order or the nonlinear feature interactions. And this work was proposed in IJCAI' 2017. More specifically, they devise by linear interaction pooling to model the second order feature interactions in a known layer. And then they stack the nonlinear layers above the by interaction layer to deepen the shallow linear FM, so as to model the high order and nonlinear feature interactions. Another representative deep learning based the factorization machine is the Deep FM, which was proposed in IJCAI' 2017. In difference from the neural FM, Deep FM integrates the architectures of FMD and the deep neural networks, so as to model the no orders features interactions like the FM, or and models the high order features interactions through the deep neural network. Note that the FM component and the deep component share the same feature embedding. Actually, there are two main benefits. First, it can help learn the lower and high order feature interactions from the raw features. Second, there's no need for the expertise feature engineering of the input as required in the wide and deep we introduced at the very beginning. Okay, in some scenario, like in the social network sites, such as the Twitter, Facebook, or Weibo, social friends of users can provide another source to benefit the user's representation learning. In the social network scenarios, both direct and the distant neighbors can help capture the user's preferences, especially when considering the information diffusion process, as well as there exist the users who have very high reputation. So in this slide, we introduce a typical social recommendation methods called the DSCF, short for the Deep Social Collaborative Filtering, which was proposed in the RESIS in 2019. In this model, they first generate some social sequence via the random walk techniques in the user's social networks. And then they mainly employ the bidirectional non-short-term memory network, the LSTM, with the hierarchical attention mechanism to capture the social information from the social sequence. Such a design has two advantages. First, they can consider the information from not only direct neighbors, but also the distant neighbors. And the bi-LSTM can help capture the bidirectional influence among the direct neighbors and the distant neighbors in the social sequence. Second, the hierarchical attentions can help differentiate the important weight of the element in a social sequence, as well as the important weight of different social sequence. On the other hand, in social recommendations, the user's representations in the item domain and the social domain should be heterogeneous. That is because user may behave and interact differently in these two domains. Then employing a unified user representations may restrain the user's representation and learning in each domain. So it's desirable to learn the separated the user representation in item domain and the social domains. To address these issues, we introduce another deep social recommendations. They solve for the deep adversarial social recommendations, which was proposed in IJCAI' 2019. To achieve the goal, and they use a bi-directional mapping operation with reconstruction between these two domains, such that they can cycle the knowledge between them to progressively enhance the user representations in both domains. However, for optimizing the ranking tasks in the recommender systems, most existing methods adopt the negative sampling techniques, which is quite ineffective. For example, in this figure, we have one male and one female. When trying to optimizing the ranking task with the negative samples, easy and unrelated negative sample can be generated, like the red dress for the male and the man warning for the female. This may be helpful at the very beginning of the training process, but later, these easy and unrelated negative samples are unable to provide useful information to further improve the user and item representation learning. Therefore, in this work, they propose to harness the power of the adversarial learning, the generated adversarial networks done to dynamically generate the informative negative samples to better guide the learning of the users and the item representations. Here, let's look at the framework of the proposed model. It consists of three main components. In the middle, this is the cyclist user modeling. We have already mentioned. They just do the knowledge transformation in both domains. Item domain adversarial learning and the social domain adversarial learning are on either side. The item domain adversarial learning on the left consists of a generator and a discriminator. And the discriminator in item domain is used to distinguish the real user and item pairs from the fake user item pairs. Is generated by the generator. So that means the discriminator aims to distinguish whether the user item pair are related. For specific users, the generator in item domain aims to approximate the underlying distribution of items. Then generate the most relevant one. And we define the generator here using the software map function over all the items according to the transferred the user representations from the social domain. And at the same time, as the user item pair are discrete, here they use the Ponish gradient in reinforcement learning to optimize this generator. Next, we will introduce the sequential recommendations. A general recommender system is mainly based on the users and item interactions, as the model we introduced before. However, they may only focus on the last click of the section, ignoring the information of the whole process. That is the user's sequential behaviors. So the sequential recommendation is proposed to model such a user's sequential behavior. And it based on the macro trends, which use the sequential data to predict the next, predict users' next action given the last action. Recently, existing work employed the sequential neural networks, like the recurrent neural networks for the sequential recommendation, and obtained promising results. In particular, they propose to enhance a user's historical interactions into a vector, which can be the representation of the user's preferences. And they can use different sequential neural networks models like the GRU or the RN and make predictions based on the hidden representation. Another representative method is burst for rack, which employs the deep bidirectional self-attention to model users' behavior sequence. Actually, they are inspired by the success of BERT in the MLP area, and to model the sequential information in recommender system. Burst for rack is stacked by L bidirectional transformer layers, and at each layer, it iteratively revises the representations of each position by changing the information across all positions at the previous layers in parallel with the transfer layer. Although these deep learning paradigms have advanced recommender systems and have been widely deployed in industry, they still have some drawbacks in practice. The first one is about the recommendation policy, where most existing deep recommender systems consider the recommendation procedures as the offline optimization, and they do not focus on, they only focus on the short-term reward. And the second drawback of existing deep recommender systems is that they treat each interactions as an independent instance for prediction, and ignore the relations among instances, resulting in suboptimal predictive performance. The first challenge is about the architecture. Existing models are mainly based on the manually designed architectures, but it requires a lot of expert knowledge of deep learning and the recommender systems. It also takes a lot of time and engineering efforts. And the last challenging is the existing methods are vulnerable to adversarial attack, and attackers can generate a fake user with well-designed profile to promote or depromote the target items in recommender systems, so as to manipulate users' decisions. And the rules of themes to defend against the potential attack is to understand how attack can be performed. Okay, this is all for the fundamentals of deep recommender systems. Next part, Xiangyu will present the reinforcement learning based recommender systems to address the first challenge in recommender systems.